Hello everyone. Today we're going to present our final project on meteorite landings, which is an interactive visualization of space rocks on Earth. So I'm Bhanu and along with Atish, Vishwesh, Kenan and Praveen, we've designed an interactive dashboard that visualizes over a century of meteorite data from a planetary science perspective. Meteorites are more than just rocks from space, and many of them originated from asteroid belts billions of years ago and are associated with the origin of life. Most of these visualizations and research of meteorites are static. They are flat maps, long tables, and are lifeless. So we thought, what if we could animate Earth's cosmic theory and explore it like a living map? Our motivation was threefold. First is the scientific exploration. We wanted to understand meteorite mass, type, and fall pattern, which helps geologists and astronomers model planetary evolution and surface processes. Exploration of meteorites can also be very helpful in finding rare elements which could be valuable for industrial and space mining explorations. Second is the societal relevance. Events like the airburst in 2013 showed how important it is to track impact risk and predict the future risk. And the final one is curiosity. Meteorites are part science and part mystery. Their historical and resource value make them fascinating objects of study. The data set we picked contains data from several centuries, which helps us to visualize meteorites' falls across the world and research about their mass and classification. Through this project, we created interactive visualizations to make it more appealing to its users, bridging the gap between raw data and meaningful insights. Moving on to target audience, our dashboard serves a wide range of users. Firstly, researchers who can analyze composition and fall patterns, educators as they can bring space science alive in classrooms, then policy analysts and space agencies who can use it for impact forecasting and hazard awareness. We wanted to bring a bridge between complex data and meaningful insight for anyone curious about the cosmos. Uh, these are all the papers that we used for doing this project, and we looked at past work with great data sets but limited tools. Most projects focus on static maps, bar charts, or single variables. And we found that there were plenty of gaps, as there was no interactivity, no time-based animations, no integrated view of composition, mass, and classification. We saw this as an opportunity to fill that gap, to make something both scientifically rigorous and visually intuitive. So, to fulfill our goals, we asked a few questions. Where are meteorites most often found? How has that changed over time? What types of meteorites are most common? And what can we detect geochemical signatures across classes? The answers lay in combining geospatial, temporal, and chemical views. So coming to the data set, our data contain information like the name of the meteorite, unique ID, the major class, mass, whether it was fell or was observed during its fall, the year it was found, its latitude, longitude, and its hierarchical classification and analyzed materials. As discussed in our project proposal, we did some EDA and found out that most of the meteorite landings were recorded between 1980 to 2010. Uh, we also found that more than 90% of records are available in found category. Coming to the mega class of the meteorites, most of them were chondrites. And you can use this link if you want to dive deeper into our exploratory data analysis. Coming to the visualizations that we used in our dashboard, this is where it all comes together. First, we built an interactive map showing global meteorite landings from 1850 to 2013. You can animate it year by year, filter by class, and view trends over time. Then we used a bar chart that updates dynamically, revealing which classes dominated each year and showing spikes for rare finds linked to expeditions. Finally, a compositional heat map, which is a beautiful color-coded grid that lets you compare elemental profiles across meteorite classes. Together, these visualizations don't just show data, but they tell stories.
As mentioned in the earlier slide, we have built an interactive web-based visualization. It contains two tabs as primary. So one is the meteorite landing over the years, which includes a dynamic geospatial map along with a dynamic bar graph. and the other one is the chemical composition of the meteorite, which is shown using a dynamic heat map. So this is developed to make an interactive visualization for the users, and then it is based on a dark theme so that the it reduces the eye strain and it is visually appealing. So I'll be presenting the website now. So as you can see, the our website includes from the year meteorites landing from the year 1850 to 2013, and it has a lot of interactive features. So the first feature is a geospatial map. This has many dynamic interactive features in it. So as you can see, we can zoom in and zoom out as we like, and then when we double click on a particular point, we are able to hide or select the particular point, so that we can focus on one particular meteorite group, and then it helps us differentiate better. So apart from that, we also have built a timeline for this. So when we start the play button, we'll be able to move over the years, and the map and the bar graphs change dynamically. And even if there is a particular overlay, due to the colors and the size of the visualization, we'll be able to see the clustered groups properly so that there will be no overlaps in the data. So as you can see in this, even when we zoom in the map, we'll clearly be able to see what are the types of meteorite. And it also comes with a tooltip. It includes mass, class, super class, and mega class for the features. And moving to the bar graph, in bar graphs, we are representing the number of meteorites along with the type of meteorites. It also gives us an option to like classify. So mega class being the most granular granular type, and then next comes the super class, and next comes the major class. So based on this, the map is dynamically loaded and the bar graph is dynamically loaded along with it. So moving on to the next tab, we have the composition heat map, which shows us the chemical separation of what the elements are in a particular meteorite. As you can see, the y-axis over here is a classification of the meteorite, and x-axis is the number of elements. We have included 30 elements in this. Uh, and the the representation you see over here is the weight percentage of the particular element in the particular meteorite. As we hover over the heat map, we'll be able to see the element and the composition of it and which category it belongs to. Here also we have provided a granularity for super class and mega class depending on whichever classification you want. We can specifically drill down and then distinctly classify.
Next, I'll be talking about the key insights we were able to find from the visualizations. As you can see, deserts like Sahara, Atacama, and Australia showed high meteorite detection rates. These arid regions turned out to be ideal for recovery, mainly because the space rocks visually stood out against the light colored terrain, and the open landscapes made searching easier. As here in the geospatial map, the size of the bubble represents the mass of the meteorite. Next, Antarctica showed a large number of meteorite recoveries, but not because more meteorites actually fell there. Instead, systematic expeditions like ants led to the targeted collection, making it one of the most significant zones for meteorite recovery on Earth. When we looked at the classification, we found that ordinary chondroids dominated the data set. That made sense. They're most abundant meteorites in the solar system, and their consistent texture and moderate density made them easier to detect and classify. On the other side, rare types like achondroids appeared to be more clustered and linked to the specific expeditions. Since these originated from differentiated planetary bodies, they were often uncovered during focused specific scientific missions rather than found randomly. We also notice regional bias in certain meteorite classes. For instance, iron meteorites were highly overrepresented in the Sahara, Their density and magnetic properties made them easy to detect in desert conditions, which likely led to the skewed pattern. From a chemical standpoint, we can see that some clear patterns. Iron-rich meteorites showed clean iron or nickel signatures, reflecting their origin from planetary cores, and chondrites had a balanced mix of silicates, metals, and trace elements, matching primitive solar system material. And achondrites displayed volcanic fingerprints, high aluminum oxide and low iron, indicating formation from crustal magmatic processes. Of course, our analysis had its limitations. The temporal scope was restricted from 1850 to 2013 due to coordinate reliability. Geographic bias was present. Remote, forested, or urban areas were underrepresented, and collection efforts were heavily focused in the US and Europe. Class imbalance was another issue. Ordinary chondroids were oversampled while rarer types were sparse. Composition wise, only about 30 out of 178 chemical features were consistently reliable, especially for trace elements. And from a tooling perspective, the platform isn't yet hosted online for public access. These are some of the key references we used throughout the project. They provided inspiration, guidance, and helped us build on what's already been done in the field. That's all for our project presentation. Hope you liked it. Thank you.